In this video, I want to talk a little bit about integration strategy. We've learned a whole lot of techniques for integrating, but now when I'm given just a problem, I now have a lot of options of how I might be able to solve that. And so we really want to kind of have a thought process or a list that we go through in our mind of, what do I try first and how do I eliminate options for how I might integrate just a random integral that's thrown in front of me. So there's of course our basic integrals using things like power rule and basic formulas that we want to be able to use. But if we're looking at something more complex than that, then we want to start going through the list of techniques that we've been learning this semester. So back in Calc 1, you learned how to do substitution, and that's usually a really good place to start. I usually want to eliminate that option before I start going on to more difficult methods of integrating. Usually next I'll start looking at things like integration by parts. Am I looking at a product of two functions, or maybe like a natural log or an inverse trig function that's just by itself, because those are great for integration by parts. Is there a trig identity that I could use, maybe a power reducing rule or Pythagorean identity that I can use to evaluate an integral? If I see a fraction, I start thinking about things like partial fractions. Is there a polynomial in the denominator that is factorable? And then that might be a way that I can integrate it. And if I see roots in there, I'm thinking maybe there's a trig substitution in there, if a u substitution hasn't worked at this point. And then if all else fails, I go to my table of integrals, which is really a last resort for us. So in this video, I'm just going to go through some examples. I'm not going to work them out all the way through. I'm just going to kind of talk about that thought process behind when do I use particular methods? How do I eliminate options? So for this first one, I see a natural log in there. I see a couple of x's in there, so I think, well, okay, could I do u substitution? Yeah, u substitution doesn't really work. My options would be the natural log of x or x to the fourth, and neither one of those gives me the other when I take the derivative. So, because the derivative of natural log of x is 1 over x, derivative of x to the fourth is 4x cubed, so those aren't really going to get me anywhere. And so I start going down my list and I think, well, it is a product of two functions. Could this be integration by parts? And in fact, it could be. If I let u equal the natural log, that's usually my first choice for a u, and dv equal x to the fourth, then du would equal 1 over x, and v would equal 1/5 x to the fifth. And so if I start plugging this into the formula, u times v would be 1/5 x to the fifth natural log of x minus v du, so 1/5 x to the fifth times 1 over x dx. And so that would simplify to just 1/5 x to the fourth, which is just power rule. So I could definitely go through and finish up this problem pretty quickly, and integration by parts works perfectly here. So integration by parts would be the way that I would solve this one. This next one, well, I see a product here, so I might want to jump straight into trying integration by parts again, but I really like to make sure I've eliminated u substitution as an option first, especially with that trig function in there. So let's say I thought maybe this is a u substitution. So then I would make u the function inside of the cosine. So that would be 1 over x, or x to the negative first, if that's easier for you to deal with. And then du would be negative 1 over x to the second, or if I use the power rule on the right one here, that'd be negative x to the negative second dx. And well, look at that, I've got a 1 over x squared right out front. So this u substitution would work nicely here. I would have cosine of u, and then the 1 over x squared dx would be replaced by du, which is definitely something I know how to integrate. So this one is just a classic u substitution, despite the fact that I have a product of functions here. This next one, I have x, or cosine of 5x to the third. That is a product, but it's a power of a trig function. So that makes me think trig integrals right off the bat on this one. If I just split off, since it's an odd power, I could split off one of the cosines and then use the Pythagorean identity for the cosine squared. According to our Pythagorean identity, cosine squared is equal to 1 minus sine squared of 5x. And then I can do a u substitution on that, where u is that sine of 5x. So then du would be equal to 5 cosine of 5x dx. And I could throw a 1/5 out front to account for that extra 5. And then I have 1 minus u squared, and then cosine of 5x dx gets replaced by the du. And now I just have a polynomial that I need to integrate. So this was a trig integral and a u substitution that I did here. And I didn't even have to get very far down the list before I came up with a solution. Okay, so they're starting to get a little more complicated here as we look through these. I've got a fraction. If I think about u substitutions, yeah, not very likely. I can eliminate that one pretty quickly. I don't see a product of functions here or anything that would really work out nicely there. So integration by parts gets scratched off pretty quickly. There's no trig functions, so a trig integral also gets scratched off pretty quickly. One of the next things I want to think about, especially because there's a polynomial in the denominator, is partial fractions. Can I factor that denominator? And if I can, well, then that means I can decompose this fraction into simpler fractions and then integrate it there. So let's see if I can factor this guy down at the bottom. Well, first off, I can see there's an x in all of those terms, so I can factor an x out. And I would get x squared plus 2x minus 3 down there. And that quadratic there does factor as well. I can split this up, and I'm looking for two numbers that multiply to give me -3 but add up to 2. So that's going to be plus 3 and minus 1. So it factors completely, which means I could decompose this fraction into 3 separate fractions. So this is partial fraction. Is how I would finish that one off. Looking at another one, well, here's a fraction as well. I have a polynomial at the bottom. If I try and factor that, well, I can't think of any two numbers that will multiply to give me 5, but add up to a +4. So it doesn't factor. Which, if it doesn't factor, I can't decompose it. I can't break it up into smaller fractions. So partial fractions is out. And just trying to think of other options here. Well, yeah, none of the other options. U substitution isn't going to work here because of that x squared. Integration by parts, also not looking like a very good option here. Something that is very handy to try out, though, in these kinds of situations is completing the square. What if I complete the square in that quadratic on the bottom? Will that get me anywhere? So let's try it here. Completing the square means I take that middle term, the 4. If I divide that by 2 and square it, so if I take 4 divided by 2 and square that, 4 divided by 2 is 2, squared is 4. So that's what the constant would have to be in order for this to be a perfect square trinomial. that would factor very nicely. And well, I have a 5, so I can just split that 5 up into 4 plus 1. And now this piece right here is a perfect square trinomial that will factor into x plus 2 squared. And then I still have the plus 1 on the outside. So the question is, well, did that help me in my integral if I rewrite this in that way? X plus 2 squared plus 1 on the bottom. Well, now I look at that, and I can do a u substitution. I can say that u is equal to x plus 2, and then du would just be equal to dx. And then I have a 7 over u squared plus 1 du. And that is a formula that I can use. That is tangent inverse. So this would be equal to 7 tangent inverse of u plus c. And then I could just reverse my substitution. So I was able to use completing the square along with a u substitution and a formula, all in one problem to solve this. So it's a very nice trick to see when you see that you have, and particularly a quadratic that is not factorable. You can always try completing the square. Okay, a few more examples to run through here. Okay, this one's got a quadratic. It is factorable, but the quadratic that's factorable is not in the denominator, which tells me not partial fractions. A u substitution is not going to work here because I have x squared in both places, on the top and the bottom. Integration by parts is not looking good here because of that root. So really, the one that my mind gravitates towards is trig substitution, because I have a root of a quadratic. I have an x squared in there, and then just a constant. So that definitely pushes me towards a trig substitution. And I'm actually not even going to work anything out on that one. That one is just definitely a trig substitution that I would go with. It's just a perfect example of it. Now this next one, very similar to the first, or to the last one. I've got a root on the bottom with an x squared and a constant. This one is very tempting to go straight into a trig sub. But again, I always want to go through other options first because a trig sub is a pretty long way of solving an integral. So again, I start with that u substitution. Can I do a u substitution here? The last one it didn't work because they were both x squared. But this time I've got just a 6x up here. And so that looks a lot more promising. So let's say that I made u equal to everything inside the root on the bottom. Then du is 2x dx, taking the derivative of x squared minus 3. And well, that is something that I can work with here. I've got, if I break up that 6, I'll have an extra 3 up front, and then the x dx will get replaced by 2, or by du. And then I have the square root of u on the bottom. Now, if that still looks kind of daunting, I can always rewrite that using exponents. So this would be 3u to the negative 1/2 du. And now it's very clear to me that I could just use power rule here and then reverse my substitution. So as tempting as it might be to do a trig sub here, a u sub does work, and so I do not want to go further down that list of options to a trig substitution. Okay, one more example of figuring out which strategy to use here. Here's another one with a quadratic that has a root around it. And so I've got a lot of options that I gravitate towards. Things like the u substitution. There's nothing really going on outside of that root, so that looks very much like it's not going to work out. Integration by parts, not very good of an option. There's no trig functions. So I'm thinking, because of the root, I kind of want to use a trig sub, but it's not a binomial, it's a trinomial. in there. So the big question becomes, well, can I turn it into a binomial? Now, just looking at this quadratic, it doesn't factor, so there's no help there. So let's try what we tried a couple of examples ago with completing the square. So I'm going to take this and complete the square on it. So x squared plus 4x. Just like that previous example, I need a plus 4 here in order for that to factor as a perfect square trinomial. I only have 3. So by putting in this plus 4, I've actually added 1 inside of the root. And so if I do minus 1, that will undo that extra 1 that I added in. If I simplified it, I'd get back to 3. So this is equivalent to what I started with. The difference now is I can factor this into a perfect square trinomial. So that would be x plus 2 squared minus 1. So if I come back to the integral, now I have 1 over x plus 2 squared minus 1 inside of that root. And now it looks like a u substitution might work. If I let u equal x plus 2, du will equal dx. And I get the integral du over u squared minus 1 inside the square root. And that is something that I can do a trig substitution on, where u is equal to secant theta. So I'm not going to work out the whole thing, but that will work out now that I have completed the square. So what worked on this one was completing the square. Along with a u sub, and then a trig sub. So complicated, but still possible, which is the most important thing. So these are the kind of things that you want to kind of be running through your head as you work on a problem and you don't know how to solve it. You're not told to solve it in a specific way. You want to be able to go through a lot of different options here to figure out what the correct method would be.